Hello there, and welcome to the first of a series of webinars that SPI is hosting on to do with all sorts of laser applications. For those of you listening in Asia, good afternoon, good evening. In Europe, good afternoon, and those in America, good morning. What we want to talk to you about today is basically drilling with nanosecond pulsed fiber lasers. My name is Jack Gabstill, and I am the Vice President of Marketing and Business Development here at SPI, and I've been involved in the laser industry for close on 35 years. So I've had experience of most applications and most types of lasers. The supporting material has been generated by one of my colleagues, Adam Rozowski, who is a Senior Applications Engineer here and is very experienced in all forms of applications, but particularly laser drilling. So what we want to do is go through a quick running order with you in terms of making holes, what nanosecond pulse fiber lasers are, the kind of applications these lasers are, and the applications for drilling. Then we'll talk a little bit about the kinds of optical setups that might be used for drilling with lasers, and also the impacts of beam quality and other important parameters. And then we'd like to talk about the various drilling techniques themselves and conclude with a summary. So, as you're probably aware, there's a whole host of different lasers that are available to do drilling, and the choice of which laser you might want to use depends very much on what you're trying to achieve. For example, on the size, depth of the hole that you want to create, and the type of material that is actually being drilled. For example, drilling of deep high aspect ratio holes requires lasers with very high average powers and very high pulse energies. Not necessarily very high peak powers, but that's quite important as well. And for example, like those kind of holes used in aero engines, traditionally LPSS or lamp pump solid state YAG lasers, or now perhaps QCW lasers are being used. For non-metallic materials, sometimes you need to use different wavelengths. And so it's important to look at what's available. It's not all about IR or 1 micron. There are green lasers, UV lasers, and also far infrared, the CO2 lasers at 10.6 microns, for example. And if it wasn't just complicated enough in terms of selection of lasers, there's also the way the laser energy is actually deployed. You could actually have CW lasers as well as pulse lasers to actually drill holes and make apertures. You can just switch them on with a gated signal. But there's also millisecond, microsecond, nanosecond, picosecond, and even femtosecond lasers that can be used for drilling applications. So the choice is actually quite amazing. It's bewildering, in fact. However, none of these lasers can do everything. So you need to understand a little bit about the capabilities and capacities of the different forms of lasers. Why do we want to deal with IR? 1 micron is actually very good for the majority of metals and also for some non-metallic materials. The 1 micron fiber lasers, for example, are very commercially attractive. The cost per watt, dollars per watt, is very low compared to some other laser technologies. These lasers have a proven industrial track record in terms of their reliability, and effectively, fiber lasers tend to be extremely low maintenance. In terms of the lasers themselves, they tend to be represented by fit and forget technology. That's basically, there is no scheduled maintenance required. Pulsed nanosecond laser sources are a subset of fiber lasers, and these are particularly suitable for high volume applications, but can be limited in terms of the material thickness and the hole sizes, and in some cases the hole quality that can be achieved. But their versatility makes them ideal for many drilling applications. At SPI, we have a whole range of nanosecond pulse lasers called red energy G4. The wavelength of these lasers is 1.6 microns, and they range from average powers of just 20 watts to as much as 200 watts, with pulse energies typically about 1 millijoule, but going up to about 5 millijoules. One of the things that makes these lasers quite special is that they are a MOPA in design and mean we can change the pulse duration. And they are extremely versatile in being able to be operated from pulses as short as 3 nanoseconds to pulses as long as 2 microseconds. They also have quite a lot of peak power and can operate over a very broad range of frequencies. And some of these lasers are even available with CW modes, and all have visible pilot guides. At the moment, I'm trying to shift the page, and it's not going for me. So excuse me for 1 second. Okay, so as I explained, one of these lasers are designed as master oscillator power amplifiers. So that basically means in their design, they have a seed laser, which is directly modulated and then amplified. And what that enables us to do is create what we call pulse tune, which is an ability to change the pulse duration. And as such, we have different models with different capabilities. Some are more restricted in terms of the feature set that you can have, and some are larger. So for example, our extended performance EP series offers up to 48 optimized pulse waveforms. And that gives the user the opportunity to basically change the pulse duration from anywhere from 3 nanoseconds up to about 2 microseconds. And also these lasers can be operated at different frequencies up to about 4 megahertz on some models. The benefit of this is that you can actually start tailoring the beam shape, and you can see that you can have this high peak power at the front end of the pulse, and then you can extend the zone, the energy regime over a longer period of time. And that basically gives you this kind of nail and tail analogy in terms of the nail, the high peak power intensity at the beginning of the pulse gives you good coupling into the material, and then the subsequent tail is the energy that is then used to actually perform the work. And again, by using a combination of pulse duration, we can maintain, or by shortening the pulses in particular at higher repetition frequencies, we can maintain the high repetition rates at very high frequencies. We also have, for different applications, a whole range of different beam qualities. These are fundamental modes of the lasers, and they actually give you the ability to focus, for example, the high beam qualities more tightly. So our S-type is a truly single-moded laser with an m² of less than 1.3, while our Z is slightly, it's just off single mode, an m² of 1.6, and then we have slightly higher moded lasers which have more broader energy distributions. The benefit is that when you have these slightly higher order modes, we can actually achieve more pulse energy and more peak power. And so there is a trade-off, but the consequence is that the spot size that you can actually focus these lasers down to is significantly reduced, and that can impact their performance on certain applications. Fiber lasers are really, or nanosecond fiber lasers are proven tools for applications such as industrial marking. Most of us in industry have now come across laser marking. It is by far and away the most common way of marking metals and materials currently, displacing many inkjet applications. These lasers are also used for applications such as engraving, and you can do very deep engraving or shallow engraving, and there's applications in automotive, for example, where we can create very deep character sets up to 600 microns deep. Also, we can actually remove material in large volumes and create very, very smooth surfaces, almost polished. And these kind of lasers are used for things like mold tools for coins, for example. These lasers can also be used for cutting applications by going over the line many, many times using either repetitive routing of the laser or using oscillation or wobbling techniques to basically gouge out more material. They can be used for cutting, and the jewelry industry is a very good example where these lasers are used. They can also be used for cleaning. The ablative ability of these lasers is good for cleaning, for example, rubber flash from mold tools, rust from steels, or even zinc prior to welding of zinc-coated steel components. And even more recently, a new application has been developed for using these very short pulsed lasers for welding. But we are actually here to talk about drilling, and this is one of the original almost laser applications, which was developed goes back almost to the 1960s, where some of the first applications for industrial lasers were drilling. One of the first applications was drilling of teats in milk bottles for babies back in the 1960s. So lasers and the applications of lasers have come a long way since then. Nowadays, they're making filters, they're using drilling techniques for marking, for backlighting, cooling, for wire guiding, light transmission, weight reduction, foil perforation, texturing. There's a whole host of different applications, and it's almost limitless. The key thing to try and understand is the types of materials that you'll want to drill. A broad range of materials can be drilled with infrared laser sources, the 1 micron sources that we're talking about today. Ferrous metals are very commonly required for drilling. Stainless steel and mild steel. These are materials that have very poor conductive properties. So thermal management is actually very important when processing these particular materials. They don't conduct the heat away very well, and parts, if you have particularly high densities of holes, tend to warp. So thermal management is very important. Non-ferrous metals, such as the highly reflective materials, copper, brass, silvers, golds, again, all can be drilled, and to some extent, the thermal issues are different. However, reflection, reflectivity, and conductivity can limit the amount of processing you can do on these materials. Ceramics tend to have low absorption. Things like alumina tend to crack if you're not careful, again with thermal management, because of the low thermal conductivity. Aluminium nitride is another material, silicon nitride, silicon carbide. All of these materials are regularly drilled with lasers, and each has their own characteristics and suffer certain problems such as high or significant taper or cracking issues if you have too dense hole structures. Semiconductors, silicon, for example, mono-poly amorphous, gallium arsenide, and other semiconductor materials are all possible to drill. Again, some of these materials are easier than others, and some end up having significant tapers. Composites, carbon reinforced fiber composites, Kaptons, FR234, all of these kind of materials do have absorption at one micron. However, there is some decomposition of the composite materials, particularly at the edges, and charring. So it's a case of horses for courses, and it depends on the requirements of the holes themselves as to whether the quality that can be achieved, for example, with nanosecond lasers, is going to be acceptable. Nanosecond lasers are typically used with scanners, typically 2D scanners, but they need to be very dynamic to make fast circular movements. There's a whole host of manufacturers that make high quality, high-speed scanners, and also more sophisticated trepanning heads can be purchased, and even 4 and 5D scanners that offer improved quality to compensate for taper so that you can get parallel holes or even negative tapers. Also, something that's actually quite beneficial is the use of a gas head. In the majority of applications, drilling is done without any process head as such. It's just using a scanner that deflects the laser beam onto the surface of the material. However, if you can administer a coaxial gas jet stream, it can significantly improve the speed of processing, the removal rate in the drilling process, and also improve the quality. What it also does is it significantly improves the thermal impact of the drilling process, adding a cooling effect. More complex scanning solutions such as polygons can be used if you can achieve perforation in a single shot. These are not very good for going over the same area many times, or also for doing non-straight lines effectively. So basically, the scanner is at some point the limitation in terms of using some of the higher power lasers. So the scanners tend not to be able to move fast enough to keep up with some of the capabilities of the laser power. So we find that typically we tend to use quite low average power lasers to do most or many of the applications. Things that people need to be aware of, particularly when using scanners for drilling applications, is the scanner dynamics. Jump speed and jump delays are particularly crucial in being able to achieve good holes. And also sometimes you can get high-speed mirror resonance, which can occasionally be problematic. This picture shows some of the issues of ejector from a drilling of silicon. I believe this is, where you can see that on the top surface it's in one particular direction, and this comes from some of the scanner dynamics. In terms of the drilling process, you have to move very quickly from one hole to the next hole, and there needs to be a dwell there to make sure that the scanner stabilizes in the location. So actually, in terms of many of the drilling applications, these jump delays and jumps can represent more than 50% of the time of the drilling process. The focusing lenses are also very important. Short lenses give you small spots, and if you want to create small features, that's very important. However, one must be aware that also with the small spot size comes a very small depth of focus. Longer lenses give bigger areas, of field and also depth of field. And so if you can use a longer lens, it generally tends to be best. It's also very important to ensure that your sample is in the focal plane of the lens. And this should be checked because particularly if you're not working in the center of the field towards the edges of the field, if you're not correctly located at that focal plane, you will get changes in the beam diameter at these peripheries, which will impact the quality of the holes achieved. When you're actually processing, it's actually quite important to know where your focal position is, as this can have a significant effect on the taper and the quality of the hole itself. So it's something that needs to be monitored and looked at. Samples should have a clear area below the drilling point so that basically the ejected material can come out, or be placed on a transparent material like glass to enable light to go through. Ideally, you want clear space below it. I did mention that for many of the applications we tend to use low powers. 20 to 50 watts is quite typical. However, the higher power lasers, particularly those above 100 watts, it is important to make sure you use good quality lenses that are made of fused silica. Otherwise, you'll get focal shifts from lensing if you're not careful. This is particularly important for single-moded beams. Eventually, we get to the drilling techniques themselves, and as you can imagine, it's not straightforward. There's almost as many drilling techniques that you can have as types of lasers. So we can have very simple piercing or single pulse processing. We can have percussion drilling, which is basically multiple passes in the same location. We can have drilling which makes use of a trepanning action, where you're actually manipulating the beam at the same time to typically to enlarge the aperture or the hole. Moving on from that, you can have more sophisticated beam manipulation, which is quite often called helical drilling. Then we can simply engrave away the hole by using a hatching process to actually remove material. Or simply we can cut holes using these lasers if the hole size is big enough, or the required hole size is big enough. So single pulses, the key thing here is it's about thin materials, and here you've got an example of a copper foil, 10 millimeters thick, the kind of foils that are used in batteries today, and using a 200 watt laser with a beam quality of less than 1.6, we are able to achieve these holes using a single pulse. And here you can see in 10 micron foil, we're getting 44 micron holes at very, very high densities. So the limitation is basically about the amount of pulse energy, and the spot size is quite key here. So there'll be an optimal spot size. If we made it a little bit smaller, we can probably get through a little bit thicker, but 10 to 15 microns of metallic materials is a reasonable requirement in terms of single pulse drilling capabilities of these types of lasers. What you have to have is sufficient pulse energy and peak power to melt and remove the material. And the selection of the laser is based on the dimensions of the holes and the thicknesses. So for example, in the previous slide, I showed an EPZ, which is nearly single mode. Here we're making holes in the similar materials, copper and on the left and aluminium on the right, where the holes are now significantly in excess of 100 microns. So we're 3 to 4 times larger in diameter. We've got about four times more pulse energy, and here we're creating holes at about 40,000 holes per second in the 10 micron copper foil, and also in the aluminium foil as well. What you can see is particularly the difference in the materials here. The copper comes out quite clean. There tends to be a bit more ridging on the aluminium, and our capability to increase the density of holes is somewhat limited on the aluminium as well. We can get very high densities of these single shot holes. So much so that we can almost make transparent materials. Here you can actually see copper and aluminium foils, as discussed, 10 and 15 microns, where we've perforated using single pulses to remove up to 75% of the actual metal content. So it's like gauze that we can create, and it's a very effective, fast process with these samples being created in a fraction of a second. So percussion is basically about single shot. So thin foils, aluminium is reasonable. The beam quality has a significant impact giving the size of holes. So for example, the Z type, which is an M squared of less than 1.6, will give you a 20 to 40 micron hole. M squared of 4 to 5 will give you a bigger hole that will basically go up to about 120 microns. Pulse energies with the different beam qualities give different sizes. And also one of the things that we found is that the pulse duration can be quite significant. Some materials respond better to longer pulses, particularly for the bigger holes. So rather than going for 200 nanoseconds, you'd want to stretch the energy onto 500 and even possibly 1 microsecond to get a more consistent, better removal of the material. One of the things we can achieve in this fast pulsing and moving is that the accuracy of the delays between pulses in the MOPA means that you can very accurately stagger the rows, which basically means that creating huge arrays of holes is actually very doable. This kind of application is actually very well suited to polygon scanners. It's probably one of the only applications in drilling. So the next technique is percussion drilling, and here we're talking about drilling holes with multiple pulses in the same location. So hitting the same spot multiple times to try and penetrate through the material. On the top you can see an aluminium sheet that's been drilled with lots and lots of different holes. It's probably a little bit tricky to see, but these hole sizes, the exit hole sizes, range for anything from 5 microns to about 60 microns. And this is a kind of test sample that we do to look at the kind of hole densities and the impact of heat that we can achieve in this kind of material. This is basically, I believe, 250 micron thick aluminium. But it's not only for these kind of just metals. You can actually process coated materials. And here is an example of holes being percussion drilled through a coated battery foil cathode, where we can actually achieve very, very high quality through these kind of sandwiched metal carbon materials. Ceramics are quite often drilled, and this is a nice example of where beam quality has a distinct advantage. So on the left you can see a hole. This is all done in the same amount of time, number of pulses. So you can see that using the same optics. So you can actually see that the single mode, where the M squared is less than 1.3, you've got a very, very small spot. You end up with consequently a very small spot size, so the entrance to the hole is relatively small. And as you can see below it, we can get very, very high depth of penetration, so our aspect ratio is pretty high. If we increase or decrease the beam quality by increasing the m squared, the hole size increases, and the depth of penetration kind of changes as well over time. Looking again at a different material, this is now silicon, again using the same type of example. The difference between an m squared of 1.3 and an m squared of 2 is roughly about 30% in terms of the spot and the hole size that you can achieve. And what's interesting here in this image here is this top image is as processed, it's uncleaned, so you can just see a little bit of spatter. However, if we can put that into an ultrasonic bath, all of this material does come off and you can get clean holes. And here's an example where the sample has been cleaned. This was done with an EPL, so it's an m squared of 2, where the entry hole is slightly larger. As I mentioned previously, the impact of pulse duration is actually quite important and significant. And sometimes longer pulses are more efficient at removing material. And this is a lovely bit of experimental work that showed this really well. So all of these three pulses, the blue, the green, and the purple, have exactly the same pulse energy. But what we're doing is changing the peak power and the pulse duration to create different pulse regimes. And what you can see, you might have expected the high peak power to give you more penetration, but actually no, it's actually the longer pulses actually give you the deeper penetration into the material, showing that it's not necessarily about the peak power, but it's about balancing the pulse duration, the pulse energy, and the peak power to optimize drilling performance. Anodized aluminium, again, is another important material that is very often drilled, and I've added this particular image to actually show that we haven't damaged the anodized layer. So you can actually see the anodization on the surface, and there's very little damage to the anodized layer. So it's actually very specific in terms of drilling through the material without damaging the top surface. We've done an awful lot of work, particularly on percussion drilling of aluminium, looking at the different effects of different parameters, looking at the time to drill holes, the exit and entrance diameters. What you tend to find without using sophisticated scanner techniques or 3, 4, 5D scanner technologies, which are incredibly expensive. I mean, sometimes as much as 10 times as much as the laser itself. You tend to get a taper to the hole, and this can be impacted by several parameters such as pulse duration. We've done extensive testing looking particularly at a 5000 series aluminium, where we just used a simple 20-watt laser to actually perform large matrices of experimental holes to see if we can understand the behavior, the dynamic behavior of hole generation, the interaction of these nanosecond pulses with the holes themselves. So one of the things we can do is look at various pulse shapes and durations. So here, as previously, what we can do, well, it's actually slightly different to the silicon example where we kept the pulse energy constant. Here we're keeping the peak power constant, but just extending the pulse duration so that we have a little bit more pulse energy. And this can have a significant impact on the materials processed. We can also maintain the pulse energy by moving some of the energy from the peak at the front. So for example, from the front of the 240 nanosecond blue trace to the red trace, where we're taking the peak power and actually putting it on the end into the tail of this second 500 nanosecond pulse. So although these pulses have exactly the same pulse energy, their characteristics are hugely different and have impacts on their drilling performance. And then we can also vary the frequency. So by just changing the frequency of the pulses themselves, we can basically reduce the amount of pulse energy in each pulse, but the average power of the laser stays exactly the same. So over a constant time period, or a dwell time for the drilling period, exactly the same energy will be deposited, but it will be deposited in a different way in the form of more pulses or less pulses. And the impact here is actually quite visible in terms of the drilling performance. I'm going to come to some results for you now. So in terms of the actual hole dynamics and the dimensions, here you can actually see some traces that show that as we increase the frequency, so basically this was done with a 20-watt laser. So at 20 watts, we tend to have 1 millijoule of pulse energy. If we increase the frequency beyond 20, if we go to 40, we're effectively halving the pulse energy. So the pulses will have less energy. So what happens is, as you have smaller pulse energies, you will have a different entrance diameter. You're putting less energy in each individual pulse, and it's not burning out so much on the material. So you're changing the entrance diameter. So here again, you can actually see, for having the same pulse energies, the effect of pulse duration. So by lengthening the pulses, you're basically extending, or should I say, making the holes slightly smaller. And again, when we look at the exit diameters, we can have a similar impact. So we can control the input diameter and the output diameter to some extent by changing the frequency and also the pulse duration. Sometimes going shorter does not necessarily mean smaller holes. And here is a good example that sometimes when we go up in or go down in pulse duration, funnily enough, the diameter doesn't quite go as low as we can with some of the longer pulses. And this is more about the performance of the materials. So it's actually, we're finding that some of the materials behave differently. So the characteristics of the materials need to be taken into account. In terms of drilling time, there is very little impact on hole geometry based on drill time. The taper is typically defined by the processing conditions. That is the optical and the optical configuration and the configurations of the pulses themselves. The drilling process is actually self-extinguishing. So basically, it will create a taper, and then if you continue to push pulses into that hole, they won't widen it or change its characteristics. And this is actually shown here by the red X's and the blue diamonds, for example. This is basically the 240 nanosecond pulses operated for 2 milliseconds and operated for 6 milliseconds. So 6 times more energy was put into these particular holes with the blue diamonds, but exactly the same entrance diameter was actually achieved. And the same is true for the 500 nanosecond pulses. So, you can over process and it shouldn't impact the quality of your holes. The density of the holes can also have an effect, because what you end up having is heat accumulation, and heat accumulation can actually impact the amount of energy that's available and the dynamics of the process itself. So it's something that you need to be careful of. So if you go too close, you slightly enlarge the holes and actually create more problems, more debris as well. So it's something to be careful of. Another thing to be aware of is the impact of focal position. Typically, people tend to focus on the surface of materials. In most cases, that's the best place to be. And typically, we'd expect the focus or the process window to be within one Rayleigh length. However, we're finding that in some cases it can be significantly better. So the Rayleigh length here is basically about plus or minus 1 millimeter with this particular optical setup. But here we're seeing it extend almost to 2 millimeters before we start dropping off in terms of performance at either end. What's also interesting in looking at the exit holes from the aluminium processing is to see that we can actually reliably create extremely small exit holes that are significantly smaller than the spot diameter of the focus spot. Some holes as small as 5 microns. I'd say that that's kind of difficult to hold, but 7 to 10 is relatively easy to achieve and maintain. But what's interesting to see is there are two distinct regimes. So the first 3, where you see 4, 9, and 14, you can actually see a significant melt ring around the exit of this whole exit, which is basically material that has become molten and resolidified. Surface tension has brought it together to this nice donut. Whereas if you have bigger exit holes, more like the diameter of the actual beam itself, the 1 over E squared diameter, you can actually see that the material is ejected more forcefully, and you can see spatter generated in the bottom with droplets being generated. So those are kind of interesting observations. But we can achieve very dense hole arrays, many hundreds of holes per second, at relatively close, within 1 diameter. But what I said previously, in terms of this kind of percussion drilling application, the jumps can represent well over 50% of the processing time. So that's aluminium. We get a lot of questions about stainless steel. Stainless steel is a difficult material. It's difficult to get good quality holes. And what's interesting is fundamentally we cannot achieve as small an exit hole in stainless steel as we can in terms of the aluminium, limiting to about 15 microns rather than the 5 to 8 microns that we can see with aluminium. And this is down to the material properties. Moving on, trepanning, which is basically making circular motions to try and enlarge the hole. And here's an example where we're using a 30 micron spot to create something more like a 100 micron hole. And that basically works quite well. Again, here we're just oscillating or moving the beam around the periphery of this aperture that we're creating and generating good, pretty circular holes. What we have to do is basically drill a pilot hole, typically using percussion parameters, and then start moving the beam in circular motions to enlarge the hole. It's not a very effective technique if you want to drill a hole that's about more than 2.5 times the diameter of the spot. You need quite a dynamic scanner to achieve the small circular motions quickly and accurately. But what you do get is very good hole exits, but the entrance can be a little bit poor. Typically, we're seeing this technique being able to generate 40 to 100 micron holes with the EPZ, which is a 1.6 m squared laser, m squared of 4 up to about 250 microns. It's not necessarily a good technique for all materials. Thermal management, as we said before, can be a problem. Accumulation of heat, particularly for some ceramics, gives problems. Alumina, for example, this really does not work very well at all. As I said previously as well, using a gas assist can help cool, remove material, improve efficiency, and overcome this to some extent. A more complicated technique is helical drilling, where we're basically spiraling outwards. And here's some examples of 0.5 millimeter thick aluminium, really nice. And again, this is alumina. So we said that trepanning wasn't the best way of doing it, but helical drilling. And here we can create very dense arrays of holes in alumina. This is the standard 0.7 millimeter grade used in electronics, where we can create holes less than a diameter apart without cracking. So it's a really good process. And here you can see a pinhead. These are really quite small holes that we've created with very little debris or discoloration. And we can process things like aluminium nitride. Again, this is more than a millimeter thick, where we're trepanning or helically drilling, a range of holes of different diameters with very, very high quality. Helical, two-stage operation. First stage using spirals to remove the bulk, as many repetitions as required. Then secondary, we would use a circular motion over the whole edge to improve the edge quality. It's very good for holes above 80 microns. It's only suitable for circular holes. Good quality, slower than trepanning and percussion drilling. Can be used on pretty much all materials that we've tested that absorb the IR. But what we tend to use is different characteristics of the pulses in terms of the bulk removal and the second stage, which is improvement of the cut quality. Again, you can get very high densities. You've got very good heat management and can improve. This can be further improved by using a gas head. And what we can do is basically use this kind of helical drilling technique for making blind holes, for example, in dot matrix codes, and it can be used as a technique for marking. It's very difficult to get zero taper with conventional 2D scanners. As I said, we need 4 to 5D scanners to get no taper or even negative tapers. With nanosecond lasers, we can, as I said, use different parameters, and that kind of works well. So our laser energy can basically switch really, really quickly, and we can basically switch waveforms. Actually, it's a microsecond, as quickly as it almost between pulses. You could actually change the pulse tune waveforms. Next is engraving. Rather than drilling or helically removing the material, we can literally just mill it away or machine it away using a hatch pattern. And this is really very good for materials that are very thermally sensitive. And this is an example of carbon fiber, reinforced fiber. And you can actually see this sample is 3.5 millimeters thick. And you can see that we've actually cut away or machined away this material very accurately with very low thermal damage. We can do fun things. We can make novelty shapes. We can make hearts, stars, any shape you like, squares. What's interesting again here is that you can see that the width of the residue, the line width here is significantly less than 100 microns. I think it's about 50 microns. These are 500 micron squares, and that web is less than 100 microns. And we can consistently and accurately do this kind of processing. It's micro machining, really, but it gives you the ability to think out of the box. If you don't need a round hole, if you want something else, it can be achieved. So with engraving, you fill the drilling area with hatching, just like engraving, then improve the hole edges by doing additional passes. You can make non-circular holes, and this actually gives the best quality holes, but they have to be typically more than 100 microns. It's a lot slower than helical, but we tend to have better thermal management, and you do really need a dynamic scaler to be able to do this. Lastly, old-fashioned cutting. You can actually cut out these large holes by using the laser beam to go over the same line again and again, or by widening the line by wobbling. This is a typical anodized sheet where we've basically processed to show the different kinds of sizes of holes that can be achieved. But what you have to be careful about is thermal management with all of these kind of close, high-density applications. So, for example, the anodized layer tends to burn off the back because too much heat input is there. But we could manage this by using appropriate delays or sequencing of the holes. There was no sequencing used in these particular examples, but we would basically alternate the holes, and that would improve the quality of the back. This process is very versatile for all different kinds of applications. That was anodized aluminium. This is again aluminium, stainless steel, and copper, to give you some examples. And here you can see how, in some instances, the beam quality can be used to your advantage. This is painted steel. This is 0.5 millimeter thick steel, where a customer was particularly interested in cutting small holes without damaging the paintwork. And here we could actually do that in a cycle time of around 2 seconds without damaging. That's a bit of smoking that you can see outside that actually wipes off. But if you have too much energy, you can see you burn back the paintwork. It's a multi-pass process. You wobble for thicker materials. For big holes greater than 250 microns, it's very quick as you remove just the area that you're cutting. And it's a pretty good in terms of the quality. And in some materials, you can actually process pretty thick materials. And this is an example where we were cutting a green ceramic up to 3 millimeters thick without even changing the focal position in relatively quick time. So I like this kind of sample because it shows all the different techniques here. From percussion, where we're drilling 40 micron holes, to trepanning, those 70 micron circles, and then a whole host of helical circles going up to 500 microns in terms of diameter. And then we're a bit more creative by doing the shapes, squares, diamonds, hearts, so that we can create apertures, whatever you want. So in summary, the choice of drilling technique depends on the hole requirement. The choice of laser depends on the hole requirement. But the flexibility of the MOPA nanosecond fiber laser gives a lot of potential for process optimization and control. And red power enables the pulse characteristics, and they can be changed. And this is the right number with a switching time of 1 microsecond. So if you're operating the laser at 100 kilohertz, you could have theoretically every pulse duration and pulse condition different. As a summary, piercing single shot, about thin foils at high speeds, percussion, small holes with greater thickness because of the number of additional pulses. If you want to enlarge those holes, you can use trepanning, particularly where heat management is not critical. You need to move to helical processing for larger holes where thermal management is critical. And engraving, that's for thick materials, and it gives a really good thermal management, but it takes a long time. And for those holes that are big, you can actually potentially cut them out. So hopefully I've given you a bit of an introduction into the kind of applications of drilling, the techniques of drilling and how they are applied to the nanosecond lasers. And there are a host of applications out there. Hopefully some of you listening will have picked up on some of the opportunities that these lasers offer, and hopefully will come up with some solutions for you. So thank you very much. I know I've overrun my time, so that's always a trick. But if there are any questions, then please feel free to send them in. And I will try and get through some of them. Okay, very quickly, couple of questions here. There was a question as to which fiber model was the best for drilling. It's kind of difficult to say, but the one that we use as our workhorse it tends to be the 20-watt EPZ laser, which has 40-odd waveforms, an M squared of less than 1.6, 1 millijoule pulse, about a 10 kilowatt peak power, and we find that this tends to be the most popular laser that we use. Another question's come in about what can you do to create parallel drilling. As I've said, you know, the use of high peak power tends to give more parallel sides, but you're better off if you really want parallel sided holes to use 4-5D scanners. Another question about stainless steel. Stainless steel is one of those materials that is very challenging to cut. It is to drill. It is possible. There is no best stainless steel. They all suffer from the heat input, discoloration, bit of burring. But the best way to get a good result with stainless steel is to basically use an assist gas in with the lasers, in with the beam itself. Another question of what's the best way of getting burless drilling? And our experience is to use the engraving kind of techniques, or a very small spot, particularly the single modes give the best results for those kind of applications. But the engraving technique gives us the sharpest edge, because we can then outline on the edge with shorter pulses to remove the material slowly so that it doesn't build up. And finally, how would you generate small holes in hollow tubes? Again, you'd want a very high beam quality. So the EPS might be the best laser for this application, which is an M squared of less than 1.3. And again, gas assistance would be the best thing to use there. I've run out of time, pretty much, ladies and gentlemen. I hope that you have found that to be of use. This is the first in a series of webinars that we will be hosting. The next one is going to be on nanosecond pulsed laser welding, the new technology for thin section similar and dissimilar metal joining. I will try and get to as many of your questions after the event and try and get answers back to you as I can. But please also fill in. There's going to be a little questionnaire sent to you. If you found this of use, or if you want to give me some feedback, this is the first such webinar that we've done, so we'd value any comments that you might have. I hope you've enjoyed that. Thank you very much.